Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual landscape of 20th century mathematics, sudden years mark seismic shifts, moments when the conceptual ground trembles and the familiar contours of a discipline are irrevocably altered. The year 1982 was one such moment. Michael Friedman, in a monumental achievement, completed the classification of simply connected topological form manifolds, revealing the world of surprising simplicity, governed by a single algebraic invariant, the intersection form. This triumph, however, cast a long and perplexing shadow. While dimensions 3 and below were being tamed by Thurston's geometrization program, and dimensions 5 and above had been rendered comprehensible by the H-obordism theorem and the work of Smale, dimension 4 remained an enigmatic wilderness. Friedman's work classified the pliable, continuous forms, but provided little guidance on their rigid, smooth counterparts. The central question became agonizingly clear: does every topological landscape in 4 dimensions permit the laying of smooth pavement, and if so, is there only one way to do it? Into this state of profound uncertainty, a young Simon Donaldson delivered a result so stunning, so utterly unexpected, that it felt less like a proof and more like a revelation from another intellectual universe. His 1985 paper, Self-Dual Connections and the Topology of Smooth Form Manifolds, did more than answer a question. It inaugurated a new field of inquiry, forging an astonishing and profoundly fruitful link between the physics of gauge fields and the purest abstractions of topology. This essay will explore the intellectual currents that culminated in Donaldson's masterpiece, dissect the intricate machinery of his proof, and trace its enduring legacy, a legacy that fundamentally reshaped our understanding of the four-dimensional. The genesis of Donaldson's work lies at the confluence of several powerful streams of modern mathematics and theoretical physics. The immediate topological context was, of course, Friedman's classification. Friedman had demonstrated that for any unmodulus metric bilinear form over the integers, there exists a unique simply connected closed topological form manifold, realizing it as its intersection form. This included peculiar forms like the E-sub-8 lattice, a positive definite form which, crucially, cannot be diagonalized over the integers. A topological manifold corresponding to this E-sub-8 form was thus known to exist. The question of its smoothability hung heavy in the air. Simultaneously, a revolution was underway in differential geometry, driven by ideas imported from quantum field theory. The Atiyah-Singer index theorem had already established a deep correspondence between the analytical properties of differential operators and the topological invariants of the spaces on which they act. Physicists, in their quest to describe fundamental forces, had developed Yang-Mills theory, a beautiful geometric framework based on the concept of connections on principal bundles. The critical insight, pursued by Atiyah, Hitchin, Singer, and others, was that the equations of motion from physics, particularly the self-duality equations, selected a special class of connections whose properties were intimately tied to the underlying topology. Clifford Torbes provided a pivotal existence theorem, showing that for certain form manifolds, non-trivial solutions to these equations, known as anti-self-dual connections or instantons, were guaranteed to exist. The final conceptual piece was the notion of a moduli space, a geometric space whose points parameterize the solutions to a set of equations. The genius of Donaldson was to realize that this moduli space of anti-self-dual connections, a structure born of physics and analysis, could be wielded as an instrument of pure topology, a probe sharp enough to discern the subtle difference between a continuous structure and a smooth one. At the heart of the 1985 paper lies a theorem of breathtaking power and elegance. It states that if a compact, oriented, simply connected smooth form manifold, which we may call M, has a definite intersection form on its second cohomology group with integer coefficients, then that form must be diagonalizable over the integers. In simpler terms, it must be equivalent to a sum of positive or negative squares. This result immediately collides with Friedman's work. The topological E-sub-8 manifold, with its non-diagonalizable definite intersection form, is thereby proven to possess no smooth structure whatsoever. It is a purely topological entity, a ghost in the mathematical machine incapable of bearing a differential structure. The proof is a symphony of disparate mathematical ideas. One begins by constructing a principal bundle over the manifold M with the structure group given by the special unitary group of degree 2, or SU2. On this bundle, one considers the space of all possible connections. Within this infinity-dimensional space, Donaldson focused on the solutions to the anti-self-dual Yang-Mills equations. These equations stipulate that the curvature 2 form of the connection, F, must satisfy the condition that the Hodge star of F equals the negative of F. These anti-self-dual connections are spent because they are numerously Yang-Mills energy functional, and more importantly, the space of such solutions, After quotienting by the Akshay gauge group, forms a finite-dimensional space known as the moduli. The true brilliance of the argument unfolds in the geometric analysis of this moduli space. For a generic choice of Riemannian metric on the base manifold M and a specific choice of bundle, this moduli space, let us call it capital M, is a smooth, orientable manifold of dimension 5. This dimension is a consequence of the Atiyah-Singer index theorem. However, this moduli space is typically what geometers call non-compact. It has ends that stretch out to infinity. Furthermore, it can possess singularities at points corresponding to reducible connections whose holonomy group is a proper subgroup of the special unitary group of degree 2. Donaldson demonstrated that for a generic metric, these singularities take a very specific form. They are isolated conical points, with the cross-section of each cone being isometric to the complex projective plane of dimension 2, denoted Cp². The most profound step in the argument concerns the non-compact ends of the moduli space through a delicate and highly technical analysis involving the phenomenon of bubbling, where the curvature of a connection concentrates at a point. Donaldson proved that one end of this 5-dimensional moduli space is, in a precise sense, the original formanifold M itself. The moduli space thus becomes a cobordism. It is a 5-dimensional oriented manifold whose boundary is the disjoint union of the original manifold M and a certain number of copies of the complex projective plane Cp², each endowed with the opposite of its standard orientation. This geometric picture has immediate and powerful topological consequences. A fundamental principle of algebraic topology is that the signature of the boundary of a compact-oriented manifold is always 0. The signature of a manifold is a topological invariant computed from its intersection form. Applying this principle, the signature of M plus the sum of the signatures of the oppositely oriented Cp² copies must equal 0. Since the signature of the standard Cp² is 1, the signature of each oppositely oriented copy is -1. This forces a direct equality. The signature of the manifold M must equal the number of singular points in the moduli space. This elegant formula connects a deep topological invariant of M to account of special solutions to a differential equation on M for a manifold with a definite intersection form, like the one sought for the E8 lattice. The signature is equal to the rank of its second cohomology group. The argument, when carried through for a hypothetical smooth E8 manifold, ultimately leads to a logical inconsistency related to the properties of the cobounding moduli space. The intersection form derived from the Gorga-theoretic construction is shown to be incompatible with the known properties of the E8 lattice. The conclusion is inescapable: no such smooth manifold can exist. The impact of this result was immediate and explosive. It was the first discovered example of an exotic topological space, a manifold existing in the world of pure topology, without a counterpart in the smooth category. This discovery fractured the long-held intuition that the topological and smooth worlds in dimension 4 were largely aligned. The universe of four manifolds was suddenly revealed to be far wilder and more complex than anyone had imagined. The technique itself was even more significant than the specific result. Donaldson quickly realized that by studying moduli spaces of anti-self dual connections on bundles with different characteristic classes, he could define an entire series of new and exquisitely sensitive invariants for smooth four manifolds. These invariants, which became known as Donaldson polynomials, could distinguish between different smooth structures on the same underlying topological manifold. For example, they were used to show the existence of a countably infinite collection of distinct smooth structures on the topological manifold R to the power of 4, a result so counterintuitive it sent shivers down the spines of even the most seasoned geometers. This proliferation of exotic R4s transformed the study of four-dimensional space from a search for classification into a strange and beautiful cartography of an infinitely varied landscape. The work also catalyzed a seismic shift in the relationship between mathematics and physics. It was a spectacular vindication of the idea that the abstract formalisms of quantum field theory contained deep truths about pure geometry. This flow of insight from physics to mathematics, championed by Michael Atiyah, became a defining feature of late 20th century science, inspiring a generation of geometers to learn the language of gauge theory and string theory. The reception of Donaldson's work within the mathematical community was a mixture of profound admiration and considerable consternation. For topologists trained in the traditional algebraic and combinatorial methods of their field, the proof was an alien artifact. It relied on the formidable analytical machinery of elliptic partial differential equations, Sobolev spaces, and the delicate geometry of infinity-dimensional manifolds. Understanding it required a fluency in differential geometry and global analysis that many in the topology community simply lacked. Atiyah famously remarked that it was as if mathematicians had received a letter from a distant, hyper-advanced civilization A message that was clearly of immense importance but written in a language they were only beginning to decipher. The field of four-manifold topology was split, for a time, between the old guard and the new practitioners of these powerful Gorga-theoretic techniques. The technical difficulty of Donaldson theory was a significant barrier, and computations of the invariants were notoriously challenging. This very difficulty, however, prompted a search for a simpler, more computationally tractable framework. This search culminated in a second revolution in 1994. Building on insights from supersymmetric quantum field theories, the physicist Edward Witten proposed a new set of differential equations, the Seiberg-Witten equations. These equations, involving spinors and an abelian U1 gauge field, were significantly simpler than the Yang-Mills equations. The resulting Seiberg-Witten invariants were shown by Kronheimer and M. Roger to contain all the information of the Donaldson polynomials. Their corresponding moduli spaces were compact, eliminating the complex boundary analysis that made Donaldson's original proof so arduous. The arrival of Seiberg-Witten theory provided a vastly more accessible toolkit for exploring four manifolds, leading to rapid progress on problems that were intractable with Donaldson theory alone. This later development in no way diminishes the original breakthrough. Seiberg-Witten theory was a brilliant refinement, but it was a refinement of a paradigm that Donaldson single-handedly created. It stood on the shoulders of the conceptual giant he had erected. In conclusion, Simon Donaldson's 1985 paper represents far more than the solution to an important problem. It stands as a landmark of modern mathematics, a testament to the power of unifying disparate fields of thought. By weaving together the analytical threads of gauge theory with the topological fabric of four-dimensional spaces, Donaldson forged a tool of unprecedented power. He revealed that the continuous world of differential equations holds the keys to unlocking the discrete, combinatorial secrets of smooth structures. The discovery of exotic smooth manifolds shattered the classical picture of dimension 4, opening up a new and profoundly complex domain of study that continues to fascinate and challenge mathematicians today. His work provided the definitive proof of the path to mathematical discovery often lies in traversing the conventional boundaries between disciplines. It remains a powerful reminder that the deepest truths are often found not within the confines of a single field, but in the fertile, uncharted territory that lies between them, where the languages of geometry, analysis, and physics converge to tell a single, stunningly coherent story about the nature of space itself.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.